Okay, now we're on to our final section, our final chapter, and that is on directed graphs. I think you've probably seen directed graphs before. I'm going to introduce them first by kind of drawing the picture, and then we'll introduce the formality. So, well, for starters, we're well familiar with drawings of graphs. Here is a drawing of a graph. And we formalized, formally a graph consists of a set of vertices, a set of edges, and this incidence relation. Now, instead of this kind of picture where we're going to kind of add some information, and what we're going to do is we're going to arrange that each edge comes with an orientation, so it's kind of directed from one vertex to one vertex. So instead of an edge just being incident with two vertices, it's now going to have a direction to it. And we'll draw those naturally, just like so. I should sort of say here, personally, I find it much more convenient to draw the arrowheads in the middle of the edge. If you draw your arrowheads at the end, then you have this problem that you have these vertices that sort of get a little overloaded. Your figures tend to get a bit messy. So you'll see me draw the arrowheads in the middle. Of course, you can do what you like. The main thing I want to do here just at the start is formalize this, right? So we kind of have a sense of what this picture is, right? We're going to have a set of vertices and a set of edges, but now the edges are going from one end to another. And yeah, anyway, I just want to introduce the right formalism to discuss that. So let's go. So a directed graph or digraph, D. As before, as with the graph, it's going to consist of a set of vertices, which denoted V of D, a set of edges, denoted E of D. But now instead of having each edge, instead of describing this with an incidence relation, we are going to, I'm going to describe it with a function. So I'm not going to name the function here, but there's going to be a function that assigns each or associates each edge with an ordered pair of vertices. Assigns every edge E an ordered pair of vertices, U comma V. And we may write U comma V to describe the edge E. Right, so now what's happening is, again, we've got vertices and edges before, as just as before. It's a set of vertices, a set of edges, and now I want to have this orientation. So somehow each edge is going from one vertex to another vertex, and we're going to formally describe this by giving by way of a function. So there's a function that assigns each edge an ordered pair. And I'm not going to name this function. We're not going to operate with it. We'll just say E is the edge U comma V. Right, so if E is an edge that goes from U to V, I should add more here, but if E is an edge and we would direct the arrowhead from U to V, then we'd say E is associated with the ordered pair U comma V. So let me draw a picture here. Oops. Here's E, and here's U, and here's V. Right, so this is all I'm describing here. I want E to be associated with an edge E is an edge that goes from U to V, so E is going to be associated just with this ordered pair, U comma V. U is called the tail of E, and V is the head of E. And we say that E is directed from U to V. So this is all really stuff that we saw before. Let's see if I can get a little more space here. Yeah, there's yeah, I mean, hopefully this formalism looks natural. For convenience, we may write D equals V comma E to indicate that D is a digraph with vertex set V and edge set E. Okay, so there are a bunch of things I guess I can italicize there, but I think maybe I'll not worry about it too much. I think you know what these definitions are largely. I don't think there are many new concepts here. So again, digraph, what we're thinking of it as a network where, as before, we have vertices, we have edges, but now, unlike the undirected case, the edge goes from one of its ends to its other end, right? So every edge is going to be associated with an ordered pair of vertices. And we'll sometimes say D equals V comma E. We'll just say D equals V comma E is a digraph, and that means D is a digraph with vertex set V and edge set E. And, right, okay. And let's add some more definition. In fact, I'll just give myself some space to keep going. As before, we still have loops, we still have parallel edges, and we have simple digraphs. But parallel might not mean what you think it does. So an edge E equals U comma V is a loop if U equals V. So up here, you see that this is a loop edge here. Two edges E and F are parallel if they have the same tail and the same head. So what does that mean in our picture here? So these two edges here, these are parallel. I didn't name my vertices, but those both have the same tail and the same head, right? They're directed from the one to the other. On the other hand, these two are not parallel. Right? Those two, they're flipped, right? One ordered pair would be like U comma V, and the other would be V comma U, and those are not the same ordered pair, so those are not parallel. So let's not worry too much about what the Greeks were thinking when they, created the word parallel, or used it in a mathematical setting. This is just what we're taking it to mean. So parallel sort of means equal in a graph theory setting. So anyway, we're just going to live with this. I'm not going to try and justify it. But again, an edge of a digraph is going to be a loop if its head and tail are the same. If I give you two edges in a digraph, they're going to be parallel if they have the same tail and the same head. So they look the same. And just as we did before, a digraph is simple if it has no loops or parallel edges. Okay. Right. Okay, so that's good. Now, I've already got a drawing on the page here, so let me talk for a moment about drawings. I mean, as before, we're going to be kind of very quick to describe things in terms of drawings of graphs because it's so much more efficient, and it's really how we think. I mean, nobody wants to think about a digraph by, as some set of vertices and some set of edges and some complicated function. I mean, that's nonsense. You want to draw a little picture to get a sense of the thing. So drawings, we already know what a drawing of an undirected graph is. Drawings of digraphs are just the same. The only distinction is that if you have an edge with ends U and V, and my edge is associated with the ordered pair U comma V, then that curve that you've drawn between the point associated with U and the point associated with V, well, you give it a little arrowhead, and so that it's directed from U to V. And that's all that there is. So we've already got those things here. So this is the concept of a drawing Well, I'm a little short on room, but this is a drawing. Right, and just as we did in the setting of graphs, I hope that we will understand, a drawing is a nice way to present a graph, a nice way to think about a graph. When you want to go about and reason about it formally in your proof, the digraph is a set of vertices. It is a set of edges. It's, this function that associates every edge with an ordered pair of vertices. So that's formally what this object is, and that's what we're talking about. But of course, it's convenient to think about it and work with these things in the form of pictures. So as before, I can draw a picture and that will specify a digraph. If I label the vertices and label the edges, you should be able to tell what digraph I'm talking about. Anyway, so we have a kind of same distinction we had before in graphs, in the sense that we are going to get our intuition by drawing little pictures, but we're going to operate in our proofs formally by working with these objects as they're defined. Okay. So those are the basic definitions. Now, if I have a digraph, I can move to a graph by just kind of forgetting the orientation. And we have a name for that. That's the underlying undirected graph. Let me once again get a text box to do this. So if D, I don't know why my page is insisting on doing this. If D is a digraph, there is an undirected graph G with the same vertex and edge sets as D, that is obtained from D by associating every edge U comma V with an ordinary edge let me say this a little differently. So it's the same vertex and edge sets. It's obtained by D by just forgetting the orientations. So what are we going to do? I'm going to take an edge U comma V and turn it into an edge with ends UV. Replacing each directed edge U comma V with an ordinary edge UV. So by this I mean an edge with ends U and V. In this case, we call G the underlying graph of D. Underlying undirected graph of D, and D is an orientation of G. Okay, so let's just do a picture here. So this is pretty easy. So here's a graph. If I add arrows here, I get an orientation of this graph. This is a digraph, so here's D and here's G. And so we'd say in this picture that D is an orientation of G, or we would say that G is the underlying graph of D. G is the underlying graph of D. Okay, so thing that's probably obvious but maybe should be said out loud still is that a graph has many orientations, but a digraph has only one underlying graph, right? The digraph just has more information than the graph, right? So the graph, there you've got a graph here, it has vertices and edges. When you turn it into a digraph, you orient it, and that means you're taking each edge with ends uv and changing it into a directed edge that either has u as its head and v as its tail, or vice versa. So you're taking that pair uv and replacing it with the ordered pair u comma v, or the ordered pair v comma u. There are many ways to take a graph and orient it, but there's only one underlying graph, right? When you're going from a digraph to the underlying graph, you're just forgetting information. You're just throwing out the orientations. Now, just as we saw in the setting of graphs, there are going to be some standard digraphs. That'll be convenient for us to reference. There's a null digraph, which is the unique digraph with no vertices and edges. So the null one, this is no vertices and of course no edges. We have a directed path. A digraph is a path if the vertices can be ordered v1 up to vn, and the edges ordered e1 up to en minus 1, such that each ei goes from vi to vi plus 1. And I'm just going to draw this in the picture. Each edge ei goes from vi to vi plus 1. So ei is the edge that goes from vi to vi plus 1. And I'm going to let Pn with a little arrow on top be a directed path on n vertices. And I'm going to put directed here. Now, if I give you a digraph, it's redundant to say that digraph is a directed path. So, I mean, if when we're in the land of digraphs, I'm just going to say that's a path if it meets this description. But in some instances, you may want to emphasize that you're talking about a digraph. So if I just want to I would just want to hand you some object for the first time, and I want to indicate that I want a directed path, not a path, and I'll say the word directed. But we'll use the term path without any other modification when we're talking about a digraph that meets this description. Now, these things we've seen before, so this is going to be P1, right? That's perfectly valid. So this definition works for n being 1 or more. When n is 1, then, well, there are no edges. That's your path. Here is P2. Here is P3. And so on. I think you've got the pattern just fine. So again, these are just standard digraphs for us. These are directed paths. I'm going to just be a little efficient here. So digraph is going to be so same thing. A digraph, we will just call it a cycle. If you already know that it's a digraph, I don't need to tell you it's a directed cycle. But now the edges are ordered v1 up to vn. The edges will be ordered e1 up to en. And this is the rule for, I should have, okay. So EI is VI plus 1 for i's between 1 and n minus 1, but the edge En goes from Vn to V1, right? And and again, I'm going to use a little arrowhead on top of Cn to indicate a directed cycle on n vertices. And just as before, this definition will take starting off right at n equals 1. You know, we don't do null digraphs. I don't want to get into that business. So n equals 1 is the smallest thing where this makes sense. This definition works for n equals 1. So if n equals 1, you don't have any edges of the first type, right? So if you let I run from 1 up to 0, well, there's no I, but you do have that last one. So C1, the directed cycle, is this guy. And C2 is now got two edges that are opposite. We call these edges opposite. And there's C3. And so on. Right, not too much more to say. So again, this if we're operating in the setting of digraphs, you know, maybe I look at a subgraph of a digraph, I'm just going to say that's a cycle, and I always mean it's a directed cycle. But if it's not clear if I'm talking about a graph or a digraph, I will say directed cycle if I want to mean I have a digraph that is a cycle. And and one more. A digraph is a tournament if its underlying graph is complete. So unlike complete graphs, there are lots and lots of tournaments, lots of genuinely different non-isomorphic tournaments on 10 vertices. So for I'm not going to draw a lot of these, but for instance, this would be a tournament on 4 vertices, right? This is a graph, it's a digraph. If you take the underlying graph, that just means you kind of throw away the orientations of the edges, you're suddenly staring at a complete graph on 4 vertices. And this is what it means to have a tournament. I think the motivation here is they imagine you have a collection of players and each pair plays one another. So they play a match, and then you could take the edge and then, you know, if this pair has played one another, then you could direct the edge from the loser to the winner. Right, so you could record the information of who wins when this pair plays one another by orienting that edge appropriately. And so then a tournament would encode if you this sort of circumstance where you had every pair of players compete in a match. A tournament would encode who wins which all of those matches. And right, and that's going to do it for our standard digraphs. As before, we have some concepts like subgraph and isomorphism. I'm not going to say these things over again. I'm not going to write them down because they're just the same as they were for graphs, right? If I have 2 digraphs and you can move from one to the other by just changing the names of the edges and the vertices, then those 2 digraphs are isomorphic. That's what it means to be isomorphic. I'm not saying that definition in any big grand sense, but or I'm not formalizing that very carefully, but that's the level at which we're going to operate with it. So we have isomorphism. We have subgraphs as well. So if I have a digraph, I can delete an edge from it, and I have a new digraph. If you want to delete a vertex, then you need to remove all of the edges that have that vertex as the head or the tail. And that gets you a new digraph. So those are all subgraphs of the original. Something that is a little bit different in our digraph setting is vertex degree, right? Because now at a vertex, I mean, we have two kinds of edges coming in, right? There are edges that have this vertex as the tail and edges that have this vertex as the head. And so when we go to talk about degree, we're going to want to make a distinction there. So we're going to define the degree degree plus of V. This is called the out degree. This is the out degree of V. This is the number of edges with tail V. Degree minus of V, this is the in degree. This is equal to the number of edges with head V. And now we have a theorem that's kind of like our first theorem for graphs, but it's even easier in the digraph setting, so I'm going to make even less out of it. For every digraph, if I give you a digraph D equals VE, then when you sum up the out degrees of all the vertices, you get the number of edges, and that's also what you get when you sum up the in degrees. And the proof here is really straight away, right? For each edge has one tail and one head. It's directed from its tail to its head. That means every edge is going to contribute 1 to the sum on the left. When I add up the out degrees, I'm adding up the every time a vertex V is a tail. When I add up the sum on the right, I'm adding up all of the in degrees. That's all the times that a vertex is a head. And every edge is contributing 1 to the sum of the tail. Every edge contributes, one new tail and one new head. So both of these sums will equal the number of edges. So you see, when we did this in graphs, it had a little bit more interest in it, because there, when you're summing up the every edge is contributing 2 to the degrees. So when you sum up the degrees of the vertices, you're going to get twice the number of edges. But now we've split things to in degree and out degree, and every edge is just contributing 1 to the sum of the in degrees, and it's contributing 1 to the sum of the out degrees. So adding up the out degrees or adding up the in degrees will give you the count of the number of edges. And and that's our first theorem on digraphs, and that's where this lesson will stop.